Okay, this is the last example of this chapter. My plan was to finish this chapter today, and I thought I have to do more than an hour, but it seems like I can finish like on time, about within an hour. Okay, let's see. So the last example is more realistic example. Affordable Care Act was enacted in 2014. So since 2014, like health insurance was mandated in all states. So many economists are wondering what's the effect of ACA, right? So I find graph data about that. So before ACA, there were uninsured people this much. So about 13.6% had no insurance. But after the ACA, so in 2014, then the proportion of people who do not have insurance dropped to 9.9%. So this is a simple graphical illustration of what happened. But now we are going to use the hypothesis testing framework to more formally argue the effect of ACA. So first, for simplicity, I'm going to simplify the numbers, right? So first, suppose that before ACA in 2013, only 80% of people had health insurance. So coverage rate was 80%, right? And the unknown parameter, is the proportion of the health insurance coverage rate after ACA. So we know what happened before, but at that time, we are wondering, and economists have wondered, what would be the change after that, right? So we would like to test if ACA had any impact on the proportion. So whether it increased from 80% or does not change or decreased. But we, like economists, it's pretty certain that ACA would not have any negative impact. So like if the coverage rate dropped after ACA come into effect, then there should be something else. The legislation should not be negative on the coverage rate. So we are going to ignore this possibility, right? As an economist, it's sensible assumption, and so we will decide between these two hypotheses. The first hypothesis is P is simply 0.8, which means it's not different. Or if it's lower than 80%, those possibilities are included in the null hypothesis. So null hypothesis is no positive effect. There is no positive effect. And the alternative hypothesis is a positive effect. There is a statistically significant positive effect on the coverage rate. And then as you can see, it is an upper tail test. So we reject the null hypothesis if the coverage rate increased noticeably after ACA, right? Then remember, rejection means the legislation had a positive effect, and non-rejection means there is no difference. There is no positive effect. So negative effect is not of our interest. It's unlikely, not interesting, and we don't care, right? So then now look at the data. We suppose that there was a survey after ACA came into effect, and you find that 86 people out of 100 individuals had health insurance. So the coverage rate is, like from that data, was 86%. And clearly, this survey is based on binary experiment, right? Do you have a health insurance or not? Yes or no question. And using this binary variable structure, you can see that the P probability of success is the mean. So you can use the framework for population mean. And standard deviation can be calculated this way, only from the probability of success. Then, so using the standard deviation formula, you have to use the standard deviation implied by the null hypothesis, right? The null hypothesis implies standard deviation of this form. So the t statistic is observed probability minus your hypothesis, and divide by standard deviation squared sample size, which is 1.5. Okay, this is the t statistic. Then make the decision by yourself if the null hypothesis is rejected at 5% or not. You may use the t statistic approach or the p-value approach. It does not matter. I calculated the t statistic for you because the standard deviation is tricky, though we have done this several times before. So pause the video and answer. The answer is no, you cannot reject the null hypothesis. If you first remember that we are doing an upper tail test, so the null hypothesis is rejected if x bar is too large, too much greater than what you expected, what your hypothesis says. If you take the t-statistic approach, this rejection rule implies this one. If t-statistic is greater than z alpha, then you reject the null hypothesis. So z alpha is 1.64. So 1.96 was for two-tail test, but now it's 1.64 for 5%. One-tail test 5%. And t-stat was 1.5. If you compare them, t-stat is not large. So it's not large, it's okay. So H0 is not rejected. If you took the p-value approach, you're going to do it this way. Rejection rule is clear. You know how to, the rejection rule is clear, but your p-value is calculated this way on the probability on the upper tail. Probability on the upper tail is the p-value, so use a calculator. Then you will get 6%, which is also greater than the significance level, so you cannot reject the null hypothesis. So either way, you cannot reject the null hypothesis, right? And you may have used the critical value approach. I'll show you how you do it. Rejection also happens if x bar is too large. And for 5%, critical value goes this way. The plus and z alpha. There are two major differences from the two-tail test. And then it is calculated this way, and in the end, the answer is 0.8656. So 86.56% is the cutoff. If the observed probability out of 100 individuals is greater than 86.56%, then you have to admit that ACA has a positive effect, statistically significant positive effect. Otherwise, the difference increase is not statistically significant. And again, we are going to use this critical value. By the way, so this critical value is greater. The sample mean was 86%, which is smaller than this critical value. So null hypothesis is not rejected, which is consistent with the other approaches. The main purpose of calculating this is to compute the error probabilities again. right? I will have you calculate the error probabilities. First, what is the type 1 error probability? I have calculated the critical value for you. So the data are the same. It is an operative test. What is the type 1 error probability? Pause the video and choose your answer. And the correct answer is C. You do not need any algebra. Simply, you just need to apply this rule. Type 1 error probability always equals to the significance level. Without any algebra, just use this number. This is the significance level. So, this is simple answer. It's a trick. It's a trap. You do not need any algebra. You do not need any other numbers but this, right? However, type 2 error is different. It's more involved. So, like, suppose that now we specifically suppose that the coverage rate, insurance coverage increased to 90% after ACA. So the truth is 90% increase. There was a positive impact. So the null hypothesis is wrong. So you should reject the null hypothesis. So this is the correct decision. But if you don't reject, then it is a type 2 error. Remember this. So then what is the type 2 error probability in this case? And to give you a hint, use this number. Oh, but yeah, you may need to use this number somewhere. Again, pause the video and you need to do algebra for this question. The answer is A. A is the answer. It goes like this. First, we assumed 90%. The coverage rate was 90%, like increased to 90% after ACA, and then we are going to standardize X bar. X bar will be standardized using mean 0.9, right? Mean is 0.9 because this is probability of success. Mean equals to the probability of success, which is 90%. And the standard deviation is 0.3 following this rule using the binary structure. So you have to use these two numbers for standardization. So standardize X bar smaller than the critical value. This is the probability you do not reject the null hypothesis. So remember, type 2 error happens when you don't reject. So we are calculating the probability of not rejecting the null hypothesis. And standardize using 0.9 and 0.3. And then in the end, you will get 12.507%. So again, this is the type 2 error probability. Therefore, the power is the other probability, the remaining probability out of 100%, right? So 87% is the power, and 12.5% is the type 2 error probability. Okay, this is it. This is the end of chapter 10, and as you see, today we learned type one-tailed test, and the basic idea is the same as two-tailed test. There is little difference, but except for a few technical changes, but they are natural if you think about the examples and the intuition. So I hope you had enough exercise in general for general hypothesis testing concepts and practices. Okay, thank you for watching, and we will start chapter 11 next week. See you later. Have a nice weekend.